Hello everyone. Today I'm gonna continue the discussion about the resultant of two different polynomials. So we're giving two polynomials and we want to know if they are co-prime to each other. And at present we have two solutions to do that. The first one is using factorization. And the second one is using the Euclidean algorithm. Okay, but I think both of them are not cool. So let's discuss the resultant of polynomials. So the definition of the resultant is the determinant of the matrix. In our case, is A0, A1, AN, A0, A1, dot, 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 AN, dot, A0, A1, AN. And this part should be n columns, and the other entries should be 0, and another part is B0, B1, dot, dot, B, Bn, B0, B1, Bn, dot, dot, B0, B1, Bn. And the right part should have n columns. And the whole matrix is n plus n times n plus n. Okay, if you remember this whole matrix with zero interest here is the coefficient matrix of n plus n linear equations, which induced by the inequality ux fx equals vx gx, in which the degree of u is less than the degree of g, which is m, and the degree of v is less than the degree of f, which is n. Okay. And we have a theorem. Two polynomials f and g co-prime to each other if and only if the resultant of f and g is not 0. Good. Let's do some simple examples. Let fx equals x squared and gx equals x. So obviously they are not co-prime because they have a common factor x. So if we use the resultant, what should we get? Yes, f and g equals determinant. So the matrix should be the left part is just 0, 0, 1, and the right part is 0, 1, 0, 1. Other entries are 0. And the determinant obviously is 0. So according to the theorem, f and g are not co-prime. Okay, another example. So if I change gx to bx plus 1, then f and g are co-prime to each other. And let's use the resultant to check the resultant. Check the result. Yes, f and g is determinant, and the matrix. The first column is the same, 0, 0, 1, and the second column turns to be 1, 1, and 1, 1, 0, 0. And if I'm right, determinant should be I guess it's 1. Yeah, the determinant equals 1, so it's not 0, which means f and g is coprime, are coprime. Okay, according to the examples, we can see that using resultant may require more calculation than these two solutions. But the advantage of using resultant is if you have f and g belongs to some polynomials Rs, in which R is an arbitrary PID. In this case, the factorization or Euclidean algorithm might not work, but the resultant still applies. Okay, let's see some general examples. So, we'll assume R to be Cy. And I have to ignore the fact that in this case, the Euclidean algorithm still works because Cy is Euclidean domain. But I'm just gonna ignore that. So fx is x squared y cubed plus 1, and gx is y squared plus 1 x squared plus 1. And we try to calculate the resultant. In the matrix, the first column is just using the definition 1, 0, y squared. And it needs to have two columns, 1, 0, y squared. And the right part, also two columns. So 1, 0, y squared plus 1, 1, 0, y squared plus 1. Right? Sorry, that is y cubed. Okay, trying to calculate this out, we expand the determinant with respect to the last row, and we get minus y cubed 0, 1. This matrix 0 y squared plus 1, 0 squared plus 1, 0, 1. This is this element. This element we get minus 0 y cubed 0 y cubed 0, 1 y squared plus 1, 0, 1. And if you calculate this out, it turns to be minus y squared plus 1 times y squared minus y cubed plus 1. And in this case, minus plus y cubed, which is obviously not 0. So in this example, f and g is coprime. Okay, thanks.